This conference will now be recorded.
Hello everyone. Today the topics that we are going to discuss, polarity of bonds, which we have already started in last class, but we have just some initial primary idea. Okay, so we'll finish it, and after that there will be Fajan's rule, which is also related to this polarity of bonds, and if time permits we'll also see a new theory which is known as VSEPR theory. So polarity of bonds, some idea we already have in the last class. So there is no such thing as pure ionic bond or pure covalent bond, though for the sake of definition we try to define them, but ideal situation that is very rare. So in reality, no bond or a compound is either completely covalent or completely ionic. So it is always something in it is always in between situation. So we'll try to see when there is pure covalent bond, how polarity can be generated. That is one thing. And after finishing that, there is another situation where you will see if there is pure ionic bond and how some covalent character can be generated. So both are possible. Okay, from pure covalent bond, some ionic character is generated, and vice versa. That is, from pure ionic bond, some covalent character is generated. So first we will focus on how in covalent bond polarity character is generated. So these two examples we have already seen in the last class. The first example is for chlorine molecule, diatomic chlorine molecule, where both sides we have similar atoms. So in this case, polarity we cannot expect. So this is actually a condition where you can expect pure covalent bond, but mostly this type of molecules are very few are there. Suppose nitrogen or oxygen or chlorine, but mostly there will be heteroatoms, that is two dissimilar atoms. So in this case you can see H and Cl, and Cl is very electronegative compared to hydrogen. So that is why electron density closer towards chlorine, and there is a del minus sign. Del minus sign means it is not fully developed negative charge, it is partial charge, which is denoted by this type of sign. So first, partial ionic character, how it is generated in covalent bond. Okay, so two possibilities in picture you have already seen this. The first possibility, non-polar covalent bond, when a covalent bond is found between two identical atoms. So these are some of the examples. Then the shared pair of electrons, it lies exactly in the middle of the nuclei of the two atoms. So suppose this is one atom A, then there is a bond, another atom A. So the electron pair that will be exactly in the middle position. Okay, because both the atoms, their electronegativity same, so they will try to attract it, that is equal tendency, fine. But in polar covalent bond, where a covalent bond is formed between atoms of different electronegativities, now the atom which is having higher electronegativity, that will have greater tendency to attract the shared pair of electrons towards itself compared to the other atom. And as a result, what will happen? There will be distortion of cloud of shared electron pair. So that you can already see in this molecule, hydrochloric acid, H and Cl. Cl is more electronegative, so it is drawing electron density towards itself. Next. So as a result of polarization, now what will happen? Just think about HCl molecule. The molecule will possess some dipole moment. So this is a new term you are seeing here, dipole moment. So we will see because of this type of generation of polarity, a new term now we have to learn, which is dipole moment. What is dipole moment? It is the product of magnitude of the charge. The charge that is developed over the two atoms, you have to take that charge, and also you have to consider the distance between the two atoms, that is their center, or you can say center of positive charge and negative charge. So when you take the product of this magnitude of the charge and the distance, then we get dipole moment. So that is the definition of dipole moment. So here we have taken this picture. So see here, suppose this is first atom, this is second atom. So in the first atom there is generation of positive charge. Which atom, that is not mentioned, you can consider any, just You can take the example of H and Cl. So positive charge is generated, which is denoted by Q plus, and negative charge is generated, which is, though it is not fully developed charge, remember that, but here it is written Q minus Q plus, but it is not fully developed charge, but it is negative charge in the right hand side, positive charge in the left hand side. And if you consider the distance of these two, this is the distance between the center of these two atoms. Okay, so dipole moment, which is denoted by this type of mu sign, mu, that is the pronunciation, and that is equal to the charge, which is Q, separated charge, and the distance between them, which is here R. Now, what about the unit? How to understand what will be the unit for this dipole moment? So, as it is multiplication of Q and R is distance, that is fine. Okay, but another value, that is charge, that will be in coulomb. So, it is coulomb for the charge and meter for the distance. So, C into M. Now, C into M, that is coulomb, capital C, and small m is meter. When you multiply these two, it is usually expressed in d by. So d by is nothing but equal to C into M. Okay, and see here 1 d by, that is actually equal to 3.336 into 10 to the power minus 30 C dot M. Obviously, this power will be very less because we have taken it in meter. And you know the distance between the two center of the atoms, that is obviously very small. So when you express it in terms of meter, obviously the power of 10 will be very less. So that is why this type of 10 to the power minus 30, this type of figure you are seeing here. Okay. So diatomic molecules such as these examples, as you are seeing here, they will have zero dipole moment because there is no charge separation possible. Okay, so they are purely non-polar molecule. And what about these molecules? See, heteroatoms present, HF, HCl, carbon, oxygen, that is carbon monoxide, then nitric oxide, they will have non-zero dipole moment, and they are called polar molecules because charge separation is possible. Now, molecules having polar bonds will not necessarily have dipole moment. Now, this, what is the meaning of this statement? Remember, the examples of this type of diatomic molecules that you are seeing here, they are very simple. Only two atoms are there, HF, HCl, CO, NO. So only two atoms. So there is no question. I'm trying to say there is only single bond present. Bond between HF, bond between HCl. But suppose if there are more than two atoms, suppose 4 atoms or 6 atoms, then there will be different bonds. So in general, if I am writing, suppose carbon X4, X may be any other atom. That means there are total 4 carbon X bonds, right? Now individually, if you see carbon and X, there will be some electronegativity difference, and this bond there will be some polarity. But overall effect on the molecule, because in the molecule there are total 4 CX bond. So individually CX bond may be polar, but you have to consider the geometry of the molecule. It may be that the geometry is such that the dipole moment of the one CX bond, that is cancelling the dipole moment of the other CX. So as a result, net dipole moment is 0. I'm not saying it is always that is always you will have this type of phenomena. That is not necessary, but in some cases that depends on the geometry. If the geometry is very symmetrical, obviously one bond polarity that will nullify the other bond polarity, but it may not be always so. Suppose the geometry is such, this type of cancellation of dipole moment is not possible, then overall the molecule will have some dipole. But here the statement means that the molecules having polar bonds. So suppose you have taken any molecule where one polar bond is present, but that doesn't mean, you cannot predict from this information directly that the overall molecule there will be dipole. So individual bonds you have to see, you have to check what is the shape of the molecule. So all these things we have to consider, then only you can decide whether there will be overall dipole moment for this molecule or not. Look at these examples. First we have taken carbon dioxide molecule. Now carbon dioxide molecule, this is linear molecule, okay, 180 degree. This angle, if you consider, this is 180 degree. Now both side there is oxygen. Now C double bond O of the left hand side bond and the right hand side bond, because there are two C double bond, what will happen? Equal dipole moment will be there, will opposite direction. Now this arrow that you are seeing here, their direction is opposite, and this is not a simple arrow. Simple arrow we just draw like this, but in this arrow you can see there is this type of vertical line. So direction of arrow will be towards that atom which is having higher electronegativity, that means towards negative charge, okay. So see here, this type of partial charges are mentioned, and the dipole moment of, there is a dipole moment for individual C double bond, but overall as the direction is opposite, it is cancelling each other. So that is the reason here mu value will be 0. Overall the molecule, there is no dipole moment possible. Similarly, here we have taken two other molecules. This is CBr4, just like CCl4. Probably you have heard CCl4, but CBr4, that is also possible. So in CBr4, which is tetrahedral geometry, here all the angles with all the BR angle. So all these angles are basically 109 degree, which is angle of tetrahedral geometry. So that is the reason here overall dipole moment, that will be 0, because one dipole moment will be cancelled by the other. Another molecule, here we have taken acetylene. This is organic molecule. This is also the same type of case as you have seen in case of carbon dioxide. That is both side equal dipole moment, so it will cancel each other. Fine. Some more examples we'll see. The more examples you will practice, it will help you to answer problem that will be related to dipole moment. So first here we have hydrochloric acid. Obviously there is a single bond, and very simple example. So you have the black arrow that you are seeing, that is for the individual bond, and the pink arrow you can consider as if it is the overall dipole moment. Though in this case you have just a single bond, so you don't have to worry about that, whether dipole moment cancellation will be there or not. That question doesn't arise. But still we have mentioned here the pink arrow because overall dipole moment is present. Next molecule, BCl3. Now this molecule is planar. So all the atoms, 3 chlorine atom, boron atom, all are present in the same plane. And these angles are also equal. This is 120 degree. That means here cancellation is possible. So no net dipole moment, mu will be 0. Next molecule we have taken formaldehyde, HCHO. Mostly it is organic molecule. We write it as ACHO. Okay, so see here, CH bond, the arrow is from H towards carbon because carbon is more electronegative, but between C and O, now the arrow is towards oxygen. Now if you look, consider the direction. The first direction for this CH bond, that is like this. Then another CH bond, that is also towards upper side, and C double bond, that is already there. So overall effect of all these dipole moment, if you consider, the overall effect is shown by this pink arrow. So here you can expect net dipole moment, that is possible. Then for ammonia, which is also tetrahedral, just like you have seen in case of the previous molecule in the previous slide, which is CBr4. But remember here in the fourth position, there is actually lone pair present. 3 nitrogen hydrogen bond and 1 lone pair is present. Now if you look at the bonds, there are 3 nitrogen hydrogen bond, and all the arrows, their direction is towards nitrogen, so as if they are accumulating towards nitrogen, right? So overall effect, it will be to that is a dipole moment overall direction that you can see from this pink arrow. Next we have CCl4, which is just like CBr4. You can also consider it is like NH3, but in NH3 there is total 3 NH bond, and the fourth position there is lone pair, but in this case we do not have any lone pair. And look at these arrows, if you focus on the arrow direction, you will be getting the idea why the overall dipole moment is 0. But in CCl4, if one chlorine is replaced by one hydrogen, now the scenario is different. Now see, for this 3 CCl bond, the direction is towards chlorine because chlorine is more electronegative than carbon. And if you consider hydrogen carbon bond, now the direction is towards this. So what will happen? Overall direction of dipole moment, it will be like this. Okay. Next molecule is PF5. Now PF5 is having this type of geometry. Suppose you have a triangle like this. In the middle position there is P and 3 F atoms, they are present here. So I'm writing the bonds and the 2F. So all these 4 atoms are a particular plane, and if you consider the plane of this triangle, and now just imagine a plane which is perpendicular to this. Now if in this plane, if you draw 2 vertical lines, one PF bond, another PF. So here the molecule, there are 2 types of PF bond. So all these PF bonds, they are in the triangular face, and these 2 are axial to each other. But what will happen? They can interchange their position. So this axial fluorine, they can interchange with equatorial. So overall effect, what will happen? Now there, that is overall effect, that is all PF bonds as if they are equivalent. And if you look at the arrow, see the direction of arrow, it will be obviously from phosphorus towards fluorine, right? So that is why you can see the direction of arrows, they are cancelling each other, and as a result the overall effect, it will be that there is no tail type. Then the next molecule which is more symmetrical, if you compare with PF5, SF6. Now SF6 is having octahedral geometry. Octahedral means something like this. Suppose I am drawing a square plane where sulfur is present at the middle position. If you join these 4 corners, all these angles are 90 degree, and there are 2 vertical bonds. So these 2 position also fluorine can remain. But if you look at the molecule, this is actually overall very symmetrical molecule. And you can also consider the direction of the arrows. It will be from sulfur towards fluorine because fluorine is more electronegative. So they are cancelling each other, and as a result there is no net dipole moment possible. Some organic molecule here you can see, we have taken here ethylene dichloride. Ethylene is C double bond, and there are 4H. You know this molecule ethylene in organic chemistry. Now 2 hydrogen, if we replace by 2 chlorine, you get cis ethylene dichloride. But if you replace any 2 hydrogen that are in trans position, now you will get trans ethylene dichloride. So when it is trans, now look at the arrow direction from carbon towards chlorine, because chlorine is more electronegative. So there will be cancellation, but cancellation is not possible in case of cis form, and this is the overall dipole moment direction. Okay, so this molecule is having some dipole moment, but the trans form, there is no dipole moment. Okay, next we have taken, it is a phenol type of molecule, but in phenol there is only one OH. In this case you have 2 OH group, and both are in para position. So both the molecules are basically 1,4 substitution, but still there is some difference. It depends on how you are drawing the oxygen hydrogen bond. So oxygen hydrogen bond, if the direction is C, opposite to each other, here the direction is like this, here it is like this. So in this case, cancellation of dipole moment will be there. But if you consider the other one, here their direction is towards same side. So in this case, dipole moment will be there, but this is 0. So how you are drawing the bonds, depending on that also, dipole moment may be present or may not be present. And one interesting example where we have taken 1,2 disubstituted compound, Now it may be not necessarily it is 1 2. This is actually 1 2, which we called ortho. This is 1 3 substitution, that is meta, and this is 1 4 substitution, that is para. Okay, so these two para carbon chlorine, their direction, it will cancel each other, so it will be 0. But once you are moving from 1 4, that is from para to meta, now, and also ortho, dipole moment cancellation of these two bonds, that is not possible, and in both cases there will be dipole moment. And if you want to know that which one will be having more dipole moment, is the ortho substitution, because now they are close to each other, that is dipole moment will be high compared to the meta form. So now until this slide we have seen how ionic character can be generated, or better I can say how polar character can be generated in covalent bond. That is the first point. Now the second point is, now partial covalent character will be generated in ionic bond. So suppose you have ideal ionic bond, you know how it is, and there is generation of covalent character. So now we will be discussing something which is reverse of the previous phenomena. So here we look at this picture, we have cation and we have anion. So this is purely ionic pair, because there is no such sharing. One is has completely donated, another one ion is completely accepted. And you can see there is difference in size, because anions are always written in a bigger sphere. Now what will happen? Because of a phenomena which is known as polarization, we will obviously see in detail what is polarization. So in polarization, what happens? The negative charge cloud that is present in the anion, in this case you can see it is a green sphere. Now this electron density, it is in the second picture, there is some polarization. So this, from this picture you can understand what is polarization. If you follow this dotted line, it is maintaining the sphere, this is dotted line. But if it is crossing this dotted line and it is reaching towards this cation, that is the electron density is now from symmetrical electron density, now it is becoming deformed. It is no longer symmetrical, so it is approaching towards cation. So now you can understand there is some covalent type of character generated. So more is the polarization, the mode will be the covalent character. So this is the in-between situation. But if you consider this picture, now the polarization is even greater. It has completely that is connected with this positive. So now see, in the compare with the first picture. In the first picture, these two are isolated. There is some electrostatic interaction that is obviously present, but electron density is not shared. Sharing, this term we use only for covalent bond. But in ionic bond also, if there is this type of sharing is happening, negative charge cloud approaching this positive charge, so there is some type of sharing is happening because of this polarization phenomena. Okay, so in this way covalent character can be generated in ionic bond. Now in the previous case we have seen that when in pure covalent bond, when polarity character generated, or you can say ionic character generated, how that happened, then we have checked the electronegativity difference. More is the electronegativity difference, more will be the polarity character generation. But in this case, how you will understand that if you have ionic bond, pure ionic bond, and then suddenly polarization is happening, you are getting some covalent character, how you will understand that, how this is happening, and when it will happen, when it will not happen, and if it is happening, in which case it will be more, in which case it will be less. All these things we have to understand. So in an ionic bond, there is an electrostatic attractive force present between cation and anion, that we know. Now this positively charged cation, it attracts the valence electrons of the anion, and also remember there is simultaneously there is repelling the nucleus, resulting a distortion. See here, this positive sign and negative sign that you are seeing here, that is because of the positive charge. It is not the positive nucleus center. Okay, it is a charge. But individually, if you consider any atom, in the center there is nucleus. I am writing here N, so that if I write positive you will be confused with the positive charge. I am writing N, that means it is nucleus, and in nucleus there is proton, so there is positive charge. Now that is common for both cationic side and anionic side. So when they are coming close to each other, it is true there is electrostatic interaction between the positive charge and negative charge. But if you focus on the nucleus, which is positive, so the positive repulsion will also be there. So this is also present, and simultaneously there is also interaction between positive and negative. So both are present together. The positively charged cation attracts the valence electrons of anion while repelling the nucleus, resulting a distortion in the electron cloud. So see, because of this polarization there is distortion of electron cloud happening, and as a result this density of electron, it is drifting towards cation, which results in some sharing of valence electrons. That is, in this way the covalent character is induced. Now you cannot say it is pure ionic bond, right? So thus a partial covalent character is developed between them, and this phenomena is polarization. Now the ability of the cation, that is how much it can polarize, that is the ability. So ability of the cation to polarize an anion, that is called the polarizing ability of the cation, and the tendency of an anion to get polarized. Tendency of the anion to get polarized by the cation, that is polarizability. So we have learned three new terms. The phenomena is polarization, and from the point of view of cation, as it is attracting the negative charge towards it, it is the polarizing ability of the cation. And from anion point of view, as it is getting polarized, it is attracted towards the positive charge, and because of that electron density is now deformed, polarization happening. So this is called polarizability. So when this type of electron that is deformed, suppose the you have taken two examples. In both the example, cation is fixed. You are just changing anion. Suppose you have taken KCl and KBr. Cation is fixed, anion is different. Now you have to consider polarizability of Cl minus Br minus. Higher is the polarizability, higher will be the polarization phenomena. Similarly, take two examples where the cation is fixed. Sorry, anion is fixed. Suppose you have taken NaBr and KBr. So in both cases, anion side is fixed, because we are now trying to compare how these two cation, their polarizing ability, how it will affect. So K plus and Na plus, their polarizing ability may not be same, because now you have taken different cation. So in this way, how to know when you are having 3 to 4 compounds, how to compare in which case this polarization will be high, in which case it will be low. So to know that is the extent of polarization, if we want to predict, we have to take the help of Fajans rules. Okay. So a few ionic bond, they have partial covalent character. But remember, that is not always necessary. But in some cases, partial covalent character can be generated. And to understand the extent of this type of covalent character generation, then we have to consider Fajans rule. Now the rule says the first point, we have to consider size of the ions. Now in case of cation, when it is very small, then its polarizing capability that will increase. Okay, and from the point of view of anion, larger the size of anion, then polarization possibility will be high. So cation must be small. The more small, better it is. That is, more covalent character will be generated. And from the point of view of anion, if it is very large, then electron density deformation, that will be facile process. Okay, so greater covalent character will be generated. So this is the first point, size of the anions. Cation must be small, anion must be large. So here we can see example. We have taken some compound, sodium fluoride, then sodium chloride. So all are having same cation. You are just changing the anionic part. You are changing from F minus to Cl minus to Br minus to I minus. Now cation is same, so you have nothing to do with the cation. You just have to focus on anion. Larger the size, more would be the covalency. Therefore, the order of covalency, it will be like this, because according to this rule, higher is the size of anion, better will be the polarization phenomena. That means maximum covalent character will be generated in sodium iodide. It is true, all of them are ionic. But as we are discussing generation of covalent character, and on the basis of Fajan's rule, you can predict in which case extent of polarization will be max. And that is possible in case of sodium iodide, because I minus size is large. So I minus, after that the next ion is Br minus, right? Then the next size is for Cl minus, and the smallest one is F minus. So because of this type of size difference, maximum covalent character Ni, and then it will decrease as you are moving towards sodium fluoride. Another example. Now we have taken some compounds where cation is differing, because we want to see how by changing the cation polarization is changing. So that is why we have fixed the anion. It is same for all, but cation is different. And if you see, all the metals are there from group 1 metals, alkali metals. So anion is same, and among the cation, smaller the cation, better will be polarization. So that is the reason, as we know, in alkali metals, when you move down the group, the first element is lithium, then sodium, then potassium, then rubidium, and then cesium. That means we know when we are moving down the group, size increases. So maximum size will be for cesium. So it will show least covalent character. So this is the order. Okay. Next point is charge of the cation. Now this point is solely based on cation. We are not discussing anything about anion. The first point, there are mention of both, but now just focus on cation. What is the charge present in the cation? Suppose you have taken two examples. In both cases, anion is same, because you are comparing charge. You have to fix the anion. If you are changing both of them, comparison is difficult. That is not possible. So if you want to know the effect of charge, you have to fix the anion, and you just have to change the cation. In one cation, suppose 2 plus charge, another cation suppose plus 1 charge. So obviously the cation which is having high charge, greater the charge of cation, greater will be polarization, and greater will be covalent character of the ionic bond. So what example we have taken? Again we have taken 3 chloride, but anion is fixed. And obviously the number of anions will change because oxidation state is different. So sodium, group 1 metal, so it is +1. Then magnesium, it is group 2, it's having oxidation is 2+, and for aluminium it is 3+. So the charges, you can see it is changing from sodium to Mg to Al. Anion is same, you don't have to consider anything for anion. But since the charge of the cation increases in this order, Na plus, then Mg2 plus, then Al3 plus. So that is the reason. Now covalent character, that will also follow the same order. So maximum covalent character you can expect in AlCl3, because in this case the cation is having maximum charge, which is +3, right? So next point, electronic configuration. Now this point is also based on cation. Suppose you have two cation. In one cation, and these two cation that you have taken, both are having same charge and size. Because see, if you are comparing two cation where anion is fixed, and you are now we are now discussing electronic configuration rule, but you already seen that size of cation matters, smaller better, charge of cation matters, greater charge greater covalent character. Now you have reached the third point, so you have to freeze the first 2 points, then you can compare electronic configuration. Okay, because all these are parameters, you are comparing the third parameter, so obviously the first 2 parameters you have to fix. So you have taken two cation, both are having similar charge and size must be close to each other. Under that condition, suppose one cation is having this type of configuration, n minus dx, x may be any number of electrons, so x is written in general way. I have not mentioned d2 or d3, it may be anything. N minus 1d having x number of electrons and ns. That means this is the principal quantum number and n minus 1 is the previous one. So if it is 4s, 4 is n value, so n minus 1 will be 3. So it is 3d4s. So when this type of configuration is present, or it may be 4d5s or 5d6s, okay? And this type of configuration, when you get it in case of transition elements. So when you have this type of configuration and another cation is having ns2np6 core electronic configuration. What is the meaning of core electronic configuration? ns2np6 is basically noble gas configuration, isn't it? So ns2np6 noble gas configuration, if it is present in the electronic configuration of the metal. Suppose you have taken sodium. Sodium is having atomic number 11. Last noble gas neon having atomic number 10. So how we write the electronic configuration of sodium after neon? You write 3s1. That means the electronic configuration of neon is ending at 2s2, 2p6, the last electronic configuration. So it is matching with ns2np6. So for sodium, the core electronic configuration is ns2np6. This is the core electronic configuration, or you can write it like this. So when you are having these two types of metals, one is from S block, it is also true for any group 2 metal. Suppose if you have taken Mg, which is having atomic number 12, then after neon it will be 3s2. So just suppose you have any alkali metal or alkaline earth metal, group 1 metal or group 2 metal, and you have another cation which is from transition element, but the configuration is like this. Okay, so what will happen? Then the configuration which is the first type, n minus 1 dx n0, it will have greater covalent character compared to the cation which is having ns2np6 core electron configuration. So this is the outermost configuration and this is the core configuration. And this is typical for alkali or alkaline earth metals, that is group 1 and group 2. Fine. So example you obviously see. Before that, here we have dipole moment related question. Okay. Here some compounds are given. Consider the following compounds. They are in liquid form. Though you can think oxygen how it is liquid form, but you have to consider it as if it is in liquid form. We can change the state by changing pressure, temperature. Okay. So suppose all of them are liquid configuration and they are flowing from this type of burette like this. These are the drops. Now you have taken a charged comb. There is electron present, so it is negatively charged. Okay, or whatever it is, that is not important. But it is charged comb is brought near their flowing stream. So if suppose the comb is not present, then the stream that is from the burette, it will be like this, vertical. Okay, but when there is a comb, the direction will change like this towards comb. Initially it was vertical, but now it will be moving towards comb. because it will be attracted towards charge. And when attraction is possible, or better I say when deflection is possible, they themselves should be having some polarity. So this question is designed in indirect manner. If it is directly asking that among all these molecules in blue color that you are seeing here, which one will be having some dipole moment, then it is a very flat question, straight question. But it is asking in a different way. It is asking all of them are in liquid form, they are flowing dropwise from burette, and how many of these molecules will show deflection when you have taken a charged comb near them. So it is another way of asking how many of these molecules will have dipole moment. So this is an integer type of question because you just have to mention a number. So here we have 1, 2, 3, 4, 9 out of 9. How many will be having dipole moment, that we have to check. So see, if you consider H2O2, so here the pictures I have mentioned, that is to some extent different. So H2O2, it is not linear. Just think about a book. When you open a book, suppose this is one page, this is another page, two planes are there. So H2O2, it is having one wedge bond in one plane, another wedge by another plane. So it is not linear, and that is the reason whether it is in gaseous phase or solid phase, and also in liquid phase. Though in gaseous and solid there is hardly any difference, only the difference in this angle. But whatever it is, important point is this molecule, it will have dipole moment. It is not that net dipole moment is 0. Okay. If it is a completely linear type of molecule, this cancellation of individual HO bond is possible. But in this case, cancellation not possible. So it will be, and that is how many of them will show deflection. So obviously it will show deflection. Okay. So I am giving a tick mark. Next is CHCl3. Now CHCl3, this example already we have discussed. Here direction, it will be for these 3 CCl, it will be like this. And for HCl, HC, that is also towards chlorine. So here also mu net dipole moment will be there. CCl4 is completely symmetric, that we have seen, it is tetrahedral, all the angles are same. Then if you consider benzene, it is a planar molecule, so no question that it will have dipole moment. But if there is some chlorine substitution present in benzene ring, not 2 chlorine atoms, only 1. So the direction of carbon chlorine bond, that will be like this, which is not cancelled by any other bond. So this should also show that is this type of deflection. And what about O2? This is completely symmetric, it will not show. HF will show. Okay. H2O will also show. Ammonia molecule, the picture we have already seen. So I'm not showing it here. But if you are curious about water molecule is HOH, and there is a particular angle and 2 lone pairs. So the direction of one HO bond, it will be from H towards oxygen. Another, so it is not cancelling each other, there will be net dipole. So HF will show deflection, this will also show deflection. Okay. So only polar molecule will be attracted towards charge comb due to the formation of electrically charged droplets in the polar liquid stream induced by a nearby charged object. Now the liquid that will show deflection, that are mentioned here, 1, 2, 3, 4, 5, 6. So here oxygen, it will not show. Then the next 4 will show. Okay. Then not CCl4, not this. So how many will show? HF, H2O, NH3, H2O, H2O2. Then chloroform and this one. 2, 3, 4, 5, 6. So out of this 9, only 6 will show this type of deflection. Answer will be 6. Each of the following options contains a set of 4 molecules. If you look at the option A, B, C, D, in each option there are 4 molecules and none of these molecules are repeated. Okay, so basically 4 in each 4 option, 4 into 4 total 16 molecules are there. Identify the option or options. Sorry, here. So it may be more than one. So you have to choose those option or options where all 4 molecules possesses permanent dipole moment at room temperature. So individually you have to check. Just take one by one all the options. Individually you have to check, and in which option all the molecules must show dipole moment. Then only you can choose that option as answer. The first one is BF3. The picture we have already seen for this molecule. Then O3. Now O3, it is not like oxygen, there is some angle present. SF6 is octahedral, remember, and XCF6, it is also just like that. So if you look at these molecules, this is planar trigonal, we have already seen its picture. This mu value 0, this is not 0 because of this type of angular shape. Then again octahedral SF6, this is also 0 just like SF6. So only this one is showing, that is ozone is showing dipole, permanent dipole. So this cannot be correct option. Next we have SO2, sulfur dioxide. Now this is again having some angular shape, so that is why it will be having net dipole moment. This is also having net dipole moment. Then we have ACH2, or you can say selenium hydride. This is also just like, remember water molecule, I have already drawn it in the last slide. So it will have some similarity because oxygen, selenium, they are from same two. It will behave closely. So same type of picture you can see, just you have seen in case of water. And then we have BRF5. Now BRF5, it is not like of SF6. In SF6 there are total 6 SF bond. Cancellation is possible, but in this case, this part there is no bond. Okay, so cancellation of charge will not be there. It is not symmetrical structure, so it will show dipole moment. So in this option you can see all of them are showing some dipole moment. So this will be correct, but we also have to check because it may be more than one, multiple correct choice, not a single option. More than one option may also be correct. Okay. One thing I would like to mention that here, if you are thinking how to decide that SO2 is angular or O3 is angular or BF3 it is diagonal planar, that answer basically you can give only after learning VSEPR theory. So that will probably start in the next class. So once you know the VSEPR theory fully, you will be able to predict their geometry or shape, and when lone pairs are present, when they are not present. So by applying that theory, you can draw their structure, and once you draw the structure, then you can easily understand overall dipole moment will be there or not. Okay. For simple molecule, you can directly draw, but for some cases, you first have to apply VSEPR theory. Okay. So next one, NO2 ammonia. So NO2 is again angular. So I'm not now going into the details why it is angular, why ammonia is tetrahedral. That answer obviously will be easily understand only after learning VSEPR. Then we have POCl3. So POCl3, this is also not symmetrical. Here the angle will be from phosphorus towards oxygen, and for individual phosphorus chlorine, the angle will be like this. But remember, though the directions are opposite, you have to remember this is not symmetrical. Okay, so it is not like CCl4 or CBr. So overall dipole moment will be there. Similarly, CH3Cl, you know, CHCl3, that example we have seen. But when it is CH3Cl, then also overall dipole moment will be there. So this is the direction for CH and this is the direction for CCl. So all are as if accumulating towards same side. So in this case also, all the molecules, they are showing dipole moment. So this is correct. B, C both. D also you have to check. BeCl2, this is linear. So this bond and this bond, they are cancelling each other. This is non-polar. CO2 we already know. This is very common example. And BCl3, it is just like BF3, similar case, trigonal pair. So that is why it will be non-polar. And we also have CHCl3. Don't confuse with CH3Cl, though it is true that in both the molecules, overall dipole moment is present. Okay. So here also it will show polarity. But except CHCl3, these three are not showing any dipole moment, so this is not correct. So how many options are correct? Among A, B, C, D, 2 options are correct, B and C. So these two problems, last two problems that we have seen, that is based on dipole moment. Now the problem that we are going to see, that is based on Fajan's rule. So we now have to apply Fajan's rule. So Fajan's rule, the first two rules, that is the size of the cation. Remember, cation and anion, cation should be small, anion should be large. And the second point is size of cation should be, charge of the cation should be smaller. And the third point, remember, that is based on electronic configuration. So here also we have to consider the same thing, electronic configuration. So now you can, so in that slide where Fajan's rule is present, I have not mentioned any example for the electronic configuration, but now you can understand it. After discussing this question, that will be clear. Assertion reason type of problem. In assertion, the statement is saying that compounds of mercury 2+ ion, which is metal, having ionic radius of 116 pm picometer, are more covalent in character than those of calcium 2+ ions with almost identical size. That means here charge is same, 2+ for both. Size are also same. Don't think that it will be exactly equal. It is more or less equal. So it means identical size. So this information is given in the assertion. Okay. And in reason, it is mentioned for two ions of the same size and charge. So Hg2+ and calcium 2+, their size and charge both are same. One with having this type of configuration and will be more polarizing than a cation where this type of electronic configuration is present. Okay. Now, if you are thinking what is this N-1 N-1 P6, just remember in case of sodium what we have written, that after neon we have 3s1. Remember what I have said. Now neon configuration, what it will be, that is the outermost neon configuration, it is 2s2 2p6. Now the principal quantum number for sodium is 3. That means here n value is 3. This is n value. So n-1 will be 2. So see, n-1 H2, n-1 P6, that is actually mentioned here. But where we have seen the rules, there it is mentioned in a different way. But actually it means the same thing. Okay. Don't think it is different electronic configuration. Here this NS0, that is directly for this 3s1. But in the slide where I have mentioned the rules, there it is mentioned NS2 NP6 core. So there the n value is basically this n-1. Okay, but whatever it is, it must be from group 1 or group 2. So it is more polarizing. Now this statement is basically correct. And it is also mentioned compounds of Ag2+ having ionic radius of 116, they are more covalent in character than those of these ions with almost 114 and the same charge. Okay, basically this is repeated here, is same statement. So assertion is basically correct, and reason, that is also obviously it is correct because it is Fajan's rule. Fine. Now, and this is also exactly explaining. So you can say that it is the correct explanation for the statement which is mentioned in assertion. Now, if we want to see what is their electronic configuration. So this is the electronic configuration for neutral Hg and neutral Ca. So when it is Hg2+, this will be 0. When it is calcium 2+, this will be 0. So calcium is having atomic number 20. Sorry, argon is 18. So this is 20, 2 extra electron, and Hg is basically 80. So after xenon, which is 54 atomic number, there will be 14 plus 10, 24, 2 more, that is 26. 54, 26, it is 80. So in this way, you can see it is basically, if you already know that Ag is from transition element and it is having this type of configuration, if you know that, that is fine. But if you only know the atomic number of Ag, then you can first write the electronic configuration. So you just have to know, if it is 80 atomic number, what is the last noble gas? Last noble gas is xenon, 54. So that is why you have to arrange the rest of the electrons in this way. Okay. And for calcium, as it has atomic number 20, last noble gas is argon. So after argon, 2 more electrons that will be present as 4s2, because argon is ending at 3s2, 3p6. So just see here the electronic configuration, it is matching with this type of electronic configuration where this part is coming from argon. And for Hg, n-1 d10, 4f is also present, but just focus on this. 6 is n, so 5 is n-1. So this type of configuration is present. So that is why Ag will be the compounds of Ag that will be more covalent in character. So here assertion and reason individually they are correct, and reason is also the correct explanation for the assertion. So this will be the correct option. So we will end here, and we are at the end of the session. Thank you for listening.